A fire-retardant coating is a protective surface layer applied to substrates, steel, wood, textiles, plastics, composites, etc., that reduces flammability, slows fire spread, and minimizes smoke/toxic gas release. Unlike conventional paints or sealants, these coatings are engineered to actively intervene in the combustion process. Mechanisms of fire-retardant coatings. Fire-retardant coatings work through one or more of these mechanisms. Thermal insulation forms a barrier that reduces heat transfer to the substrate. Endothermic decomposition. Fillers like aluminum hydroxide, ATH, or magnesium hydroxide, MDH, absorb heat and release water vapor, cooling the surface. Char formation. Carbon-rich components form a protective carbonaceous layer that insulates and blocks oxygen diffusion. Intumescence. Intumescent coatings are a fascinating area of fire-retardant coating technology. They're engineered to swell and form a protective char layer when exposed to heat or flame, insulating the substrate steel, wood, composites, textiles, etc., and delaying structural failure. How intumescent coatings work. When heated, 200 to 400 degrees Celsius, the coating undergoes a chemical transformation. Acid source, for example, ammonium polyphosphate, AAPP, decomposes to form phosphoric acid. Carbon source, for example, pentaerythritol, starch, lignin, dehydrated by the acid, forming a stable char. Blowing agent, for example, melamine, urea, expandable graphite, releases gases, nitrogen, ammonia, carbon dioxide, that cause the char to swell, foam into an insulating layer. The result is a multicellular, expanded carbonaceous foam that blocks heat and oxygen, reducing substrate temperature rise and delaying ignition/structural collapse. Categories of fire-retardant coatings. Non-intumescent fire-retardant coatings. Rely on inorganic fillers, ATH, MD, H, zinc borate, TiO2, nanoclays. Mechanism, cooling, oxygen dilution, barrier formation. Used in plastics, adhesives, cables, and electronics. Cementitious or mineral-based coatings. Contain gypsum, Portland cement, or lightweight aggregates. Provide passive fire resistance in tunnels, buildings, industrial plants. Intumescent coatings. Swell when exposed to fire, creating a thick insulating char. Typical use: steel structures, wood, and composites. Specialty: high-performance coatings. Silicone-based thermal stability for aerospace/automotive. Epoxy-based structural fire protection plus anti-corrosion. Polyurethane/acrylic systems. Flexible flame-retardant films for textiles and plastics. Additives and fillers commonly used. Flame-retardant fillers are widely used in coatings and adhesives to suppress ignition, slow flame spread, and reduce smoke/toxic gas release. The right additive depends on performance requirements, processing, cost, and whether halogen-free formulations are desired. Phosphorus-based ammonium polyphosphate, APP, melamine phosphates, DOPO derivatives. Nitrogen-based melamine dicyandiamide. Inorganic fillers, ATH, MDH, zinc borate, expandable graphite. Nanofillers, layered silicates, graphene oxide, silica nanoparticles. Bio-based, chitosan, lignin, phytic acid, eco-friendly char formers. Applications: structural steel, intumescent epoxy or acrylic coatings, 2 to 3 hour fire protection. Wood and furniture, intumescent paints, halogen-free clear coatings. Electronics and cables, halogen-free flame-retardant coatings, APP plus nanoclays. Aerospace and automotive, silicone/epoxy hybrids with nanofillers. Textiles and flexible materials, PU/acrylic coatings with expandable graphite or phosphorus nitrogen systems. Challenges and trends. Durability, outdoor exposure, need for weather-resistant binders. Mechanical integrity, swollen char layers can be brittle, reinforced with nanoparticles. Eco-regulations, shift away from halogenated flame retardants. Focus on phosphorus, nitrogen, mineral, and bio-based systems. Smart coatings, dual function, anti-corrosion, plus fire retardant, self-healing coatings. Summary: fire retardant coatings are engineered protective finishes that prevent or delay ignition and fire spread. They work via intumescence, thermal insulation, char formation, or endothermic cooling. The field is moving toward halogen-free, nanocomposite, and bio-based formulations with improved durability for sustainable fire safety.